Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics from University of Delhi. Today we are going to discuss about the module Transducer Part 3 from the paper Measurements and Instrumentation. In this module, we will study about transducer operation and theoretical background behind conversion of energy from one form to another. Here we will study about LVDT that can convert any linear motion into an electrical signal. Then we will study about inductive transducers and followed by capacitive transducers. The main application of transducer is the measurement of non-electrical quantities by using various electrical methods. The use of electrical methods to measure any non-electrical quantity continuously and transmit data over long distances with high accuracy and sensitivity is the preferred method to record and investigate a phenomena of interest. Few advantages of measuring a non-electrical quantity via electrical methods are automatic measurement and constant readiness of the measuring apparatus. Second, the possibility of non-inertial reproduction of varying value of quantity under investigation. It opens the possibility of automatic mathematical processing of the results of the measurement. Instrument having wide range of measurement can be easily developed. Here onwards, we will study about transducers like LVDT, inductive transducers, etc. for measuring different types of non-electrical mechanical motions of the object of interest. A student of electrical measurement method should note that transducer converts energy from one form to another. It may be electrical, mechanical, thermal, pressure, etc. Whereas a transformer is a static electrical device with an inductive coil that can transform electrical energy inductively. Whereas a transformer is a static electrical device with inductive winding coils that can transform electrical energy inductively. Linear variable differential transformer. Linear variable differential transformer is an inductive transducer that converts the linear motion into an electrical signal. LVDT is a differential transformer that consists of one primary winding P and two identical secondary windings S1 and S2 wound over a hollow bobbin of non-magnetic and insulating material. An illustration is shown in figure 1. Both windings have equal number of turns and are arranged concentrically and placed on the side of the primary winding P. Attached to the sensing element is a soft iron core whose displacement is to be measured. It is shaped in form of cylinder or rods and slides freely in the hollow portion of the bobbin. To avoid eddy current loss, nickel iron alloy is used as a core material which is positioned longitudinally. Primary windings is connected to an AC source whose voltage is varied from 5 to 25 volt and frequency range is from 50 Hz to 20 kHz. When core moves in the bobbin, it varies coupling between primary and secondary windings. In the central position, the coupling between the two windings is equal, and so the output between the coupling is also equal. As the core moves towards the left of the central position, the magnetic linkage between S1 increases and with the secondary winding S2 increases. This increase increases output voltage in S1 and decreases output voltage in S2. An opposite effect will happen when core moves towards right of the bobbin. Both the windings are connected in series position. This produces a difference in the voltage output voltages of secondary windings and gives the measurement of displacement. The differential output voltage produced with the displacement of core in LVDT is explained by the curve in the figure 2. From the curve 1 can observe that the linearity is limited to certain range of displacement, that is 5 mm on either side of the null position, beyond which the curve tends to flatten out at both ends. The range of linearity of the curve is limited by the dimension of the transducer. The net induced EMF, that is E0, with the displacement of the movable core can be calculated from the following expression. E0 in brackets j omega is equals to j omega IP into brackets 4 pi np ns mu naught bx. This is divided by 3m ln into r naught divided by ri. This term is multiplied with 1 minus xr square divided by 2b square. This is equation 1, where omega is equals to supply frequency in radians per second, IP is the primary current, NP and NS are number of turns of the primary and the secondary windings. R0 and Ri are outer and inner radii of the coil system. X is equals to the displacement of the core from the null position. Mu naught is the absolute permittivity of the free space, that is 4 pi into 10 raised to the minus 7 h pi m. At null position, the output voltage is not zero. Some residual current exists at the output terminal, but is less than 1% of the maximum value of the output in the linear range. In commercially available transformers, displacement from the null position varies from plus minus 0.01 mm to plus minus 25 mm. LVDTs are used where displacements are too large for strain gauges to handle. They are used for measuring displacements from fraction of a millimeter to few centimeters. If LVDTs are used for displacement greater than 25 mm, then an appropriate gearing system should be used. They can also be connected to other transformers. They are often used for measuring pressure, force, weight, etc. Inductive transducer. An inductive transducer belongs to the category of analog passive transducer. They normally operate on one of the following principles. First is variation of self-inductance of the coil. Second is the variation of mutual inductance of the coil. And third would be production of eddy current. Let us look at these principles one by one. Transducer operation via variation of self-inductance. Self-inductance of the coil is given by the expression L is equals to N squared divided by small l, that is divided by mu a. This is equals to N square into mu a divided by small l. This is equals to N square mu g. This is equation 2, where N is the number of turns in the coil, Small l is the mean magnetic path length, A is the cross-sectional area of the magnetic path, and mu is the magnetic permeability of the material. Geometric form factor G is given by A divided by small l. The self-inductance can be varied by changing the number of turns in a coil with permeability of magnetic material and by altering geometric configuration of the magnetic circuit. An inductive transducer can be used for measuring linear as well as angular displacement. Transducer operation via variation of mutual inductance. This type of transducer works on the principle of mutual inductance between the two coils, which further depends on the self-inductance of the coils and coefficient of coupling between them. This relationship can be understood with the following expression: M is equals to K multiplied by root of L1 into L2. This is equation 3, where K is the coefficient of coupling and L1 and L2 are self-inductances of the coil. Transducers where two or more coils are used, mutual inductance between the coils is varied as per the measurand. A simple example of inductive transducer for measurement of linear displacement is shown in figure 3. Here, the transducer coils are in series, so inductance is sum of self-inductance of both the coils and the mutual inductance between them. Mathematically, inductance in this arrangement varies from L1 plus L2 minus 2M to L1 plus L2 plus 2M. The displacement of the moving iron piece creates changes in the air gap of the magnetic circuit. This change in the flux with the movement of iron piece results in mutual inductance between the coil. This mutual inductance can be sensed by the bridge circuits. Transducer operation via production of eddy current. Eddy currents are also called Foucault currents. They are loops of electrical current induced within the conductors in presence of changing magnetic field. In such transducer, a conducting plate is kept near the coils carrying alternating current, and eddy current is induced in the conducting plate. This plate produces its own magnetic field in opposition to the magnetic field created by the coil. Thus, the currents induced in the plate reduce the net flux associated with the coil. This reduces inductance of the coil. Closer is the plate to the coil, higher is the induced eddy current, and higher will be the reduction in the inductance of the coil. Briefly, the inductance of a coil gets altered by the movement of the plate. Capacitive transducers. A capacitive transducer is a variable capacitor whose capacitance is varied by a non-electrical quantity being measured. The capacitance C for a parallel plate capacitor is given by the following expression: C is equals to epsilon naught into epsilon R into A divided by D farads. This is equation 4, where epsilon naught is the absolute permittivity of the free space, which is equals to 8.854 into 10 raised to power minus 12 farads per meter. Epsilon R is the relative permittivity of the dielectric, A is the area of plates in meter squares, and D is the distance between the two plates in meters. Capacitive transducers are also analog passive transducers. and capacitance in such transducer is varied by one of the following methods. 1. By changing the overlapping area of the plate A. Second, by varying relative permittivity of the dielectric material between the plates. Third, by varying the distance between the plates D. Any of the above change can be caused by physical variables like displacement, force, or pressure. Change in capacitance is also caused by change in permittivity that would be in case of measurements of levels of gases or liquids. Any change in the capacitance can be measured with an AC bridge having an oscillatory circuit. Transducer operation via variation of overlapping area of plates. Such transducers operate on the most basic fact that the capacitance in a capacitor is proportional to the overlapping area of plates. To understand the operation of capacitive transducer, let us consider that we have two parallel plates with a constant width B as shown in figure 5a. Length L is the overlapping portion of the plates which varies with the displacement of the moving plate. Any change in displacement changes the capacitance of the system is also given by the following expression. C is equals to absolute permittivity into relative permittivity into A divided by D. This is equals to absolute permittivity into relative permittivity into B into L divided by D farads. This is equation 5, where L is the length of the overlapping portion in meters, B is the width of the plate in meters, D is the separation distance between the plates in meters. Sensitivity S of the system is given with the differential of S with respect to small change in the overlapping portion of the plate. This can be written as S is equals to delta C by delta L, that is farads per meter. This is equation 6. The curve drawn for the sensitivity is between the capacitance of the transducer and the displacement. The curve is linear except in the initial portion, which is due to the edge effect. This curve is shown in figure 5b. The design of the transducer plates can be varied according to the application. Plates can be cylindrical or parallel semicircular plates. The equation of these designs can be derived by substituting values for the overlapping area in previously discussed equation 5. Transducer operation via variation in distance between the plates. Such capacitors have two parallel plates, where one is fixed and other is moving plate. Here, capacitance is measured by varying distance d between the two plates, which is proportional to the measured capacitance. This can be seen in equation 4. The inverse relationship of the curve between the capacitance and the displacement is shown in figure 6. The curve is nonlinear and the sensitivity of the system is high only for the initial portion of the curve. Therefore, this method is best suited for extremely small displacements only. For close approximation of linearity, the transducer may have thin mica, thinner than the minimum gap between the plates. Theoretically, the sensitivity of the system can be increased by increasing the area of the plates or by reducing the distance between the plates. Transducer operation via variation of permittivity of the dielectric material between the plates. In this system, dielectric material of relative permeability moves between the fixed parallel plates according to the displacement under measurement. Figure 7 shows the operation of the capacitive transducer with the displacement of the dielectric material. The net capacitance is given by the following expression. C is equals to absolute permittivity multiplied by B by D. This is multiplied by, in brackets, L1 plus relative permittivity multiplied with L minus L1 brackets closed. This is equation 7. And the small change in the capacitance with the small displacement of the dielectric material is given by delta C. This is equals to E naught, that is absolute permittivity, multiplied by B into X divided by D. This is multiplied with, in brackets, relative permittivity minus 1. This is equation 8. Change in displacement is proportional to the change in capacitance. This method can be used to measure displacement from 1 micron to 10 mm. Applications: capacitive transducers are used for measuring force and pressure changes, which are first converted into displacement and then into change in capacitance. They are also employed to measure density, volume, level of liquid, weight, etc. But along with the mechanical modifiers. In this module, we studied about transformers like LVDT that can convert any linear motion into electrical signal. This is followed by inductive and capacitive transducers. Thereafter, we studied about transducer operation and theoretical background behind conversion of energy from one form to another.